What about the others, where they are? Okay. So write down the question. Next question from the atom. Write down the question. Define the distance of closest approach. Define the distance of closest approach. Full stop. An alpha particle of kinetic energy K. An alpha particle of kinetic energy K is bombarded on thin gold foil. Is bombarded on thin gold foil. Full stop. The distance of the closest approach. The distance of the closest approach is small r. Is small r. What will be the distance? What will be the distance of closest approach? Closest approach for an alpha particle. For an alpha particle of double kinetic energy. Of double kinetic energy. So I'll repeat this question. Define the distance of closest approach. An alpha particle of kinetic energy K is bombarded on the thin gold foil. The distance of the closest approach is r. What will be the distance of closest approach for an alpha particle of double the kinetic energy? Okay. So what do you mean by closest approach? Okay. Whenever we are doing alpha particle experiment, okay, so whenever we are performing alpha particle experiment, number of electrons, means number of particles we are bombarding on the metal sheet, okay, and whenever, suppose we have this as a gold foil, okay, so the particle, alpha particle is traveling, it reaches to the central part, okay, not exactly at the near to the plate, and it senses the heaviest portion and it retraces back. So from where it can reaches back, or we can say that the distance from the nucleus where all kinetic energy of the alpha particle is gets converted into what? Potential energy is known as the distance of closest approach. Means alpha particle, suppose it is traveling with certain kinetic energy and it senses that heaviest part, and that total kinetic energies get converted into potential energy, and that from there that reflects back, okay, that is known as the distance of closest approach. So we know that the formula for closest approach, we are denoting the closest approach by r naught, and r naught is nothing but twice k, that is k is a constant, z e square divided by, we have the kinetic energy, okay, kinetic energy of the alpha particle, okay, this is nothing but distance of closest approach. That means from here we can write the r naught is inversely proportional to the kinetic energy of the alpha particle. So here, suppose kinetic energy of the alpha particle we are making double, okay, doubled, then what will happen? They are asking here what will be the distance of closest approach of an alpha particle if we are doubling the kinetic energy. So here kinetic energies get double, that means distance of closest approach is what gets reduced by half, or it will what get halved. So we can write here r is become, or r naught is becomes half or halved, okay. So here twice is the kinetic energy, we doubled it, then R naught is what? Decreases by how much? By 2. That's it. Okay. So this is also important question. They will ask this for 2 marks. Okay. Copy this. Okay. Then now write down next question. Write down the next question. In the Geiger-Marsden experiment, calculate the distance of closest approach. Calculate the distance of closest approach for an alpha particle. With energy 2.56 into 10 raised to minus 12 joule. 2.56 into 10 raised to minus 12 joule. Consider that the particle approaches gold nucleus Z equal to 79. Z is equal to 79 in the head-on position. Okay, B part of this question, write down. If the wave experiment is repeated with the proton of the same energy, then what will be the value of the distance of closest approach? What will be the value of the distance of closest approach? I'll repeat this question. In a Geiger-Marsden experiment, calculate the distance of closest approach for an alpha particle with energy 2.56 into 10 raised to minus 12 joule. Consider that the particle approaches gold nucleus, and here Z is given, that is nothing but 79 in the head-on position. The B part, if the wave experiment is repeated with the proton of the same energy, then what will be the value of distance of closest approach? Okay. So here we know that just now we did the previous question. Whenever the particle achieves the distance of closest approach, the kinetic energy is entirely converted in the form of potential energy. So we can write here from this, means when they are using the word distance of closest approach, so in that case we can write kinetic energy is totally gets converted into potential energy, and these energies are what here say. And here in the question kinetic energy is given 2.56, correct, into 10 raised to minus 12 joule. This much is the kinetic energy given. So what is the distance of closest approach formula? We have R naught. Always write the formula. Okay. R naught is nothing but 2k ZE square divided by kinetic energy. Okay. Can you getting this? Now substitute the value. Okay. So here R naught, they are asking here the value of the closest approach. Okay. So R naught is given, and here kinetic energy is equal to potential energy. So here only by substituting here this formula, means putting the value in R naught, we will not get the answer. So we can take here kinetic energy is equal to potential energy. Kinetic energy is given 2.56 into 10 raised to minus 12. And what is the potential energy? So here suppose the sheet gold foil is there and alpha particle is bombarding over here. Okay. So in that case we can write K into 2E Z divided by, we can write it as a R naught. Okay. So substitute here. K is nothing but how much? 9 into 10 raised to 9. Okay. So into 2 charge on the particle here 1.6. So sorry, here E square is there. Okay, sorry. E square, that is 1.6 into 10 raised to minus 19 whole bracket square. Z is given, that is for gold foil is given 79, and divided by we have R naught. Okay, so here transpose R naught to this side and do this calculation. Okay, I will take R naught to this side, so you will get 9 into 10 raised to 9, 9 into 2, I will write here directly 18 into 79 into 1.6 whole bracket square into 10 raised to 19. Okay, 19 into 19, 38 minus 38 divided by, we can write 2.56 into 10 raised to minus 12. Now do this multiplication and calculate the answer for R naught. Okay, so initially we have a alpha particle here. Okay, so if you are doing this calculation, R naught we are getting approximately 14.2 into 10 raised to minus 5, so not minus 5, minus 15 meter is the R naught we are getting. Okay, this is value for R naught. So in the second bit they are asking the same experiment is performed, okay, with the same energy, what is the value, but here the alpha particle is replaced by the proton. So in case of proton, so if we are repeating the same experiment with the same energy, so this energy is what gets halved, that's it. Okay, so 14.2 into 10 raised to minus 15 divided by 2, that is nothing but 7.1 into 10 raised to minus 15. 7.1 into 10 raised to minus 15 meter is the answer if we are repeating the same experiment with the help of proton. Okay, so this is what the answer we are getting. Copy this. Okay, finished. So write down one more. I will discuss this. No need to write down this question. Write two important limitations of a Rutherford model of the atom. Okay, this question sometimes asks for 2 to 3 marks. So write the important limitations of the Rutherford model of the atom. So here stability of an atom is not explained. Okay, what he said, once the energy of the electron is get reduced or if it is gets over, then it will fall into the nucleus. Okay, that is a wrong statement. He is not able to explain that. And different line spectra in H in the hydrogen atom, okay, is also not able to observe. Means apart from the hydrogen atom, he is not able to explain the spectrum for the other elements. He only explained about the hydrogen. So these are the two main limitations you have to write for the Rutherford's model. Getting this? So write down the next question. State Bohr's quantization condition. State Bohr's quantization condition of angular momentum full stop. Calculate the shortest wavelength of the bracket series and state to which part of EM spectrum does it belong. Okay, so I'll repeat this question. Here state Bohr's quantization condition of angular momentum, calculate the shortest wavelength of the bracket series and state to which part of EM wave spectrum does it belongs? Okay. So Bohr's quantization condition is what? Okay. So we know that here this is the second postulate or second statement of the Bohr's quantization condition. We know that angular momentum we are writing as a L. Okay. And L is nothing but what? mvr. They are moving definitely around the circular orbit. Okay, and they are integral multiple of nh upon 2 pi. So we are writing L is nothing but mvr, and that is integral multiple of nh upon 2 pi. So this is nothing but what? Bohr's quantization condition. Okay, so where you can write m is nothing but 1, 2, 3 and 4 so on. Okay, so here they are saying calculate the shortest wavelength for the bracket series. Okay, yesterday we did all the 5 series: Lyman, Balmer, Paschen, Pfund and bracket. Okay, and we discussed about the their initial orbit and their final orbits, and even we learned about the shortest and longest wavelength also. Okay, so they are asking here shortest wavelength. Okay, so here shortest wavelength है तो n initial. I told you yesterday. Those who are new today, they can check the previous session. So n initial is always we are taking it as a infinity. Okay, and bracket series. So n final is nothing but how much? We have n final for brackets is nothing but 4. Okay, so we know the formula. Wavelength or wave number is nothing but r. Inside the bracket 1 upon nf square minus 1 upon ni square. Getting? And these are the conditions we got it for bracket series. Okay, and here in bracket series we know that that is lying in IR region, that is infrared region. So now substitute the value and calculate the answer. Here they are asking what? Wavelength they are asking. Okay, so here R you can substitute as 1.1 Rydberg's constant, 1.1 into 10 raised to 7. So here NF is nothing but 4 square minus 1 upon infinity. So 1.1 into 10 raised to 7 and 1 by 60. So this term will become 0. This is 1 by lambda. So if I want lambda, then 16 into 10 raised to minus 7 divided by 1.1. This reciprocally powers are also get changed. That is my positive will become negative. And if you calculate this, then you will get the answer 1.414 something, 1.45. Okay, into 10 raised to minus 7 meter. Okay, so this is the answer, not minus, minus 6 meter. And bracket series always lie in the infrared region. Infrared region. Getting this? So write down this answer. Can you getting this? How I am solving? Yesterday we already did the numericals based on the Lyman and bracket series. I hope you are getting these calculations and this type of questions. Write down next question, take a screenshot or you can take a picture of this. Okay, or those who are solving along with me, they can check the calculations. Okay, decimal points, powers, you can just check once. Okay, write down next question. A hydrogen atom. Next question is very important. Mark it as a IMP. A hydrogen atom initially in the ground state absorbs a photon which excites it to the n is equal to 4 level. Estimate the frequency of the photon. Estimate the frequency of the photon. Okay, so this is very important. See here, what are the what they are asking here. A hydrogen atom initially in the ground state, okay, absorbs a photon which excites it to n is equal to 4. Means whenever electron is transiting from lower to higher orbit, it always absorbs the energy, and when it jumps from higher to lower, then it emits the energy. Okay, so here initially it is at a ground state. Ground means 1. Okay, and it is excited to third excited level, that means n is equal to 4 here. Okay, so that is given. So they are asking here, estimate the frequency of the photon. Okay, we have to calculate the frequency of the photon. So either you can use here the formula that is 1 by lambda is equal to r 1 upon nf square minus 1 upon ni square. That is also okay. Or you can go for energy E is equal to minus 13.6 n square. Okay, so can you do that? Check once. Here we have two methods. You can use any one method. I will show you whenever this kind of questions will come, because many times you can use this formula. Okay, and here nf is nothing but you have to take 4 and ni is nothing but 1. Okay, with that also you can calculate, but here you will get lambda, then we have to calculate frequency. F is equal to c by lambda, then make that modification, you will get answer. Okay, we will solve by both the ways. So here write down, put the values and check the answer. Okay, so Redbox constant 1.1 into 10 raised to 7, nf 1 upon 4 square minus 1 upon 1 square. So here 1.1 into 10 raised to 7, so 1 upon 16 minus 1 by 1. So that is nothing but 1.1 into 10 raised to 7 into you can 16 minus 1, that is minus. So minus we are taking as a mod, then we will get 15 by 16. Okay, so you can reverse it, 16 into 10 raised to minus 7, 15 into 1.1. Okay, or you can go 16 into 160 into 10 raised to minus 7 divided by 15 into 11. Okay, calculate this, you will get directly lambda. Check what will be the answer you will get. Check the calculation. Do the calculation. Check the answer. It is approximately we will get here as 0.9696 into 10 raised to minus 7 meter. Okay, here actually we will get this as a negative, but you have to take a mod. Okay, so lambda we will get, but we want here frequency. F is equal to c by lambda. So 3 into 10 raised to 8 divided by 0.969 into 10 raised to minus 7. So 3 upon 0.969 into this 7 will go up, so it will become plus 15. So if you simplify this, you will get the answer as 3.01 something. So you can approximately take it as 3 into 10 raised to 15 hertz. This is what the answer we are getting. Understood? Okay. Or this is also one method. and another method also I will show you. By both the methods we will get the same answer. Okay, so I take a screenshot of this, then I will show you another method. Can you getting this? Okay, chalo, I will erase this. I hope everyone is took the screenshot. Now you can go by this, or you can, as they are using the word hydrogen spectrum, okay, and it absorbs and all. So we know the formula for energy. E is equal to minus 13.6 upon n square electron volt. Okay, this is what we have the formula. Okay, and what I will do now here, h nu, E is nothing but what we can write h nu, and here I will write minus 13 and 13.6 n square, that is final, minus I can write here minus of minus 13.6 Ni square. Okay, so sorry, Ni square, I will write it like this. Okay, so here minus 13.6, Nf is nothing but 4 given, 4 square, minus of minus will become plus 13.6 divided by 1. Okay, so here only I will do the adjustment. Here I will write 60. Now you can simplify by taking 13.6 out. Okay, so here 1 by 16 plus 1 by minus 1 by 16 upon 1. Okay, and you can simplify. You will get the answer again in negative. Then you can take a mod. Okay, here you will get it as minus 13.6 into 15 by 16. Okay, so then 15 by 60 electron volt. Electron is nothing but 1.6 into 10 raised to minus 19. You can substitute, and then here we have h into nu. Nu is nothing but frequency. I will keep nu as it is, and h I will transpose, and h value is 6.63 into 10 raised to minus 34. So you can do the calculation and take a mod of this answer. And here also you will get approximately 3 into 10 raised to 15 meter. Okay, you can do the calculation and check. So for this question we have two methods. You can use any one, the previous or this. Okay, any one method you can use. Getting this? Write down next one. Write down one more question. I hope everyone took the screenshot. Write down next. Name the spectral series. Name the spectral series for hydrogen atom. Name the spectral series for hydrogen atom which lies in the visible region. Which lies in the visible region. Find the ratio of maximum to the minimum wavelength. Find the ratio of maximum to the minimum wavelength of this series. So I will repeat this question. Name the spectral series for hydrogen atom which lies in the visible region. Find the ratio of the maximum to the minimum wavelength of this series. Okay, so yesterday I explained at the beginning of the session about all the 5 spectra and what is the initial and final values of the electrons, as well as I told you about the region where all these spectra or all these series are lying. Okay, so a very first statement, name the spectral series of the hydrogen atom which lies in the visible region. Okay, so out of 5, Balmer series is lying in between the visible region. Very important. एंड बाल्मर सीरीज का फाइनल जो है, फाइनल इलेक्ट्रॉन, द इलेक्ट्रॉन कैन कम और फॉल at n is equal to 2. This should click in your mind, then only you can able to find out the answer. And the next part they are asking, find the ratio of maximum to the minimum wavelength. That means we have to calculate shortest and longest wavelength for this series, and we have to take a ratio. Can you getting the question what I am saying? Okay, very easy, but we must practice this kind of question. So they are now saying visible, maybe they will ask infrared region, or maybe they ask different. Okay, so prepare that table which I already discussed in the previous session. Okay, so I hope everyone wrote the question. Anyhow, I will repeat one more time. Name the spectral series for a hydrogen atom which lies in the visible region. Find the ratio of the maximum to the minimum wavelength of this series. Okay, so by after reading this question, what are the things we understood, that you can write it down as a given. So here write down the given things. A very initial statement, that is, this is a visible region, that means this is a Balmer region, a Balmer series. Balmer series lies in the UV region, oh sorry, not UV, visible region. Okay, and we know that visible Balmer series, or always the electron can come and fall into the n is equal to 2 as a final state, and we have to take the minimum and maximum. Okay, so if we want to find out the shortest wavelength, okay, we will go for the shortest wavelength. So for shortest, nf is equal to 2 and ni is nothing but infinity. We know that 1 by lambda minimum I will write as it is shortest. So here we can write r 1 upon nf square minus 1 upon ni square. Okay. So what I will do, I will write 1 upon lambda minimum. I will not substitute the value for r, and nf is nothing but 2 square, that is nothing but 1 by 4. Okay, and I will write lambda minimum is nothing but 4 by r. I took a reciprocal and I keep it as it is. Okay, anyhow, if we are taking ratio, then r is somewhere is getting cancelled. Now we will go for longest wavelength. Longest wavelength. So longest wavelength के लिए again nf will remain same 2, but ni is nothing, right after 2 is nothing but 3. Okay, so here we will get lambda 1 by lambda max, that is equal to r. We will get 1 upon nf square minus 1 upon ni square. Okay, so once you get this, then substitute the values over here. 1 upon lambda max is nothing but r. nf is nothing but 1 by 2 square, that is 4, and ni is nothing but ni is nothing but how much? We have a 3. So 3 means minus 1 by 9. Okay, so r 9, if we take LCM, 9 minus 4 is nothing but 5, and 9 4s are 36. Okay, and I will write this as a lambda max, and this lambda max is nothing but 36 upon 5r. Now this is my equation number 2. Then lambda max to lambda mean, if I take a ratio, then 36 upon 5r into reciprocal it, r upon 4, r get cancelled. So 4, how much the 36? 4 9s are, okay, so 4 9s are 36. So 9 by 5 is the ratio for lambda max to lambda mean. Okay, so 9 by 5 is the answer. Can you getting this? Can you getting? So these all are very important question for the exam point of view. Okay, finished. So write down one more question. Write down one more question. An electron in the hydrogen atom, makes a transition from orbits of higher energies to orbits of lower energy, for higher or energies to the orbits of lower energies. First bit, when will such transitions result in first Lyman and Balmer series. Okay. Second bit, find the ratio of longest wavelength. In the Lyman series to the shortest wavelength in the Balmer series. Getting this? I'll repeat this question. An electron in the hydrogen atom makes a transition from orbits of higher energy to the orbits of lower energy. Okay. So when it is jumping from higher to lower, then it emits the energy. So first bit they are asking, when such transitions results in Lyman series, B Balmer series. Okay. And second bit, find the ratio of their longest wavelength in the Lyman series to the shortest wavelength in the Balmer series. Okay. So here hydrogen atom makes the transition from higher energy to lower. That means Lyman series is there, no? Lyman and Balmer. So Lyman, it final stage is nothing but 1, and initial is from 2, 3 and infinity. And in Balmer series also we have NF is nothing but 2 and Ni is nothing but 3, 4, 5 and so on. Yesterday we discussed. So write down this first part because that is also important. They are asking. Okay, Balmer so I already wrote here. Okay, so you can write down for Balmer. Okay, Balmer I wrote it here. So M initial only gets changed. So Balmer, the electron comes into the 2, transit into 2, and N initial is nothing but 2, 3 and so on up to infinity. And in Lyman series, NF is nothing but 1 and Ni is nothing but 2, this Ni is nothing but 3, 4. This is 2, 3 and so on up to infinity. Okay, this is the first bit. Then second bit they are asking, find the longest wavelength in the Lyman series. Okay, for I will write here Lyman series for longest wavelength. So F is 2 and longest they want no. So N initial, longest means N initial, and that N initial we are taking it as Lyman NF is 1 and Ni is nothing but 2. Okay, so longest we are taking right after that and shortest we are going for infinity. Now we have 1 by lambda max is nothing but 1 upon is equal to R 1 upon NF square minus 1 upon Ni square. Okay, substitute the value. R you can keep it as it is. NF is nothing but 1 by 1 because 1 square is 1. Ni square, that is 2 ka square is 4, 1 by 4. So take a do LCM here, then you will get 3R by 4. This is nothing but 1 upon lambda max. Okay, and if you take here lambda max reciprocal it, then 4 upon 3r. Okay, so after that we have a Balmer series, and for Balmer series they are asking us to find out the shortest, correct, shortest wavelength. So Balmer ke liye NF is nothing but 2 and Ni is nothing but 3, but shortest is there, no, that is infinity. So again 1 by lambda minimum is equal to r inside the bracket nf square minus ni square. Okay, so don't put the value for r. Nf is nothing but 1 by 4, ni is becomes 0, so 1 by 4 that is equal to r by 4. So lambda minimum, if we reciprocal it, then we will get 4 by r. Okay, and if you take a ratio of lambda max by lambda min, so lambda max I got it as a 4 upon 3r, and minimum is get reciprocal, then r by 4. So r get cancelled, 4 is get cancelled, answer is 1 by 3. This is a 3-mark question. Okay, this is 3-mark question. Mark it as a I and B. Finish this. Okay, so now I will take one application oriented question, means atom, and they are blending this with dual nature formula. Okay, that kind of questions we can take now. So write down that. You can take a screenshot. Can you getting? Okay, write down. Calculate the de Broglie wavelength. Calculate the de Broglie wavelength of the electron orbiting in the n is equal to 2, orbiting in the n is equal to 2, state the hydrogen atom, state the wavelength of the hydrogen atom. Okay, state for hydrogen atom, correct, state for hydrogen atom. So I will repeat this. Calculate the de Broglie wavelength of the electron orbiting in n is equal to 2, state of H atom. Okay, so this is the application question. This is the application oriented question. Many times there is a possibility to ask this kind of blending questions. Okay, so here I will solve. Here hydrogen atom is given. Okay, and here the electron orbiting n is equal to 2. So n is equal to 2 given. Okay, and de Broglie wavelength I know, lambda is nothing but h upon square root of 2m kinetic energy, 2m into kinetic energy, but I don't know kinetic energy. Okay, but kinetic energy is nothing but energy, that is equal to minus 13.6 n square electron volt, correct. So now here already n is equal to 2, that means we can write here 13 minus 13.6 upon 4 electron volt. We can write it like this, and electron volt you can convert it into joule by multiplying 1.6 into 10 raised to minus 19 joule. So this is nothing but what you are getting, kinetic energy, and straight away you can substitute this in the in this formula. So here I will write it, so 4, and here I will write it as a 0.4, and here I will substitute the value over here. So H is nothing but 6.63 into 10 raised to minus 34 divided by, we can write 2 into mass. Mass of what here? they are saying electron, no, mass of electron is 9.1 into 10 raised to minus 31 into kinetic energy we got it as 13.6 into 0.4 into 10 raised to minus 19. Okay, so first you can calculate the add the powers and take it out. Okay, check how much is the answer you will get. 0.4 will come out from the square root. (31 plus 19 is nothing but 15, 50, and you can take it as 50. Then you can take it out as a minus 25. Minus 25 goes up. So here I will simplify this. 6.63 into 10 raised to minus 34. This will 50. Take out minus 25. You can send up plus 25. Inside this bracket you can write 9.1 into 2. 13.6 into 0.4. So this 0.4 also you can take it out. Okay, or you can remove the decimal. Okay, and simplify this. So after simplifying you will get here something 0.67 into 10 raised to minus 9 meter. This is nothing but what your wavelength, or you can write here 0.67 nanometer is the answer. Getting this? So this is also 3-mark question, very important question. Write down this. Take a screenshot. Priyanka, are you there? Priyanka, can you able to hear me? Yes. Who all are there? Who all are there in the session? Okay, then no one is replying. Leave it. So write down one more question based on this. Calculate the de Broglie wavelength associated. Calculate the de Broglie wavelength associated with the electron. In the second excited state. In the second excited state of hydrogen atom, full stop. The ground state energy of the hydrogen atom is 13.6 electron volt. Okay, I will repeat this question. Calculate the de Broglie wavelength associated with the electron in the second excited state of the hydrogen atom. The ground state energy of the hydrogen atom is 13.6. Okay, so we are using the same formula. Okay, calculations are different. Here the electron is get excited, okay, from the second orbit. That means we have to take it as n is nothing but 3. Okay, and calculate the kinetic energy, and the de Broglie wavelength we know that lambda is equal to h upon square root of 2m into kinetic energy. Substitute the value and calculate the answer. Okay, so now here check. Same question, similar kind of question is there, but here what is gets changed. Here second excited state. Yesterday I told you second excited means n is equal to how much here? 3. Okay, so here we will get 3 square is 9. Convert this into joule. So here multiply this. So 6.68 de Broglie wavelength formula you can use. Then substitute the values over here. So 2 into 9.1 into 10 raised to minus 13. Okay, and 13.6. Not 13.6. Here the values are changed. Yeah, 13.6 into 1.6 into 10 raised to minus 19. Here 9 I will take it as a 1 by 3. Okay, so I will write it like this and then simplify this equation. Again 31 plus 19 is nothing but 50. So that 50 I will take it as a up, that is minus 50 will become plus 25 when I transpose up. Okay, 9.1 36 into, here you will get it as 13.6 into 1.6 into 10 raised to minus, oh sorry, not powers, we already took it out. Okay, now simplify this and 1 by 3 is there, that is get reciprocal here, multiplied by 3, and do the calculation and find out the answer. Okay, check this. Now in this case, if you calculate the wavelength, then you will get wavelength is nothing but approximately 1 into 10 raised to minus 9 meter or 1 nanometer is the answer. Okay, this is what we are getting the answer for this question. So in between people are coming and going, I will find it out who is attending. Okay, take a screenshot of this and then write down one question for a homework. Okay, write the question for homework. Write down the kinetic energy of the electron. Kinetic energy of the electron orbiting in the first excited state. Orbiting in the first excited state of a hydrogen atom is 3.4 electron volt. Is 3.4 electron volt. Determine the de Broglie wavelength. Determine the de Broglie wavelength associated with it. De Broglie wavelength associated with it. Okay, I will repeat this. The kinetic energy of the electron orbiting in the first excited state of hydrogen atom is 3.4 electron volt. Determine the de Broglie wavelength associated with it. Okay, so here kinetic energy is given directly, so convert that into joules and use the formula lambda is equal to h upon square root of 2m into kinetic energy and calculate the answer, and you will get the answer 0.67 nanometer. Okay, check afterwards, you can do it as a homework. So write down the next question. Write down next question. The ground state energy of a hydrogen atom. The ground state energy of a hydrogen atom is minus 13.6. Is minus 13.6 electron volt. Minus 13.6 electron volt. What are the kinetic and potential energies of the electron? What are the kinetic and potential energies of electron in this state? Okay, so solve this, try this question. I will repeat this question. what the ground state energy of a hydrogen atom is minus 13.6 electron volt. What are the kinetic and potential energies of electron in this state? Okay, yesterday in the last session we did the similar type of question. So total energy is given, that is nothing but minus 13.6 electron volt. Okay, and we know that kinetic energy is nothing but minus of total energy. Okay, so solve this, simplify this, calculate the potential energies. Okay, I will in the last session we did the last session I gave the relationship between this. So we know that here total energy is given, that is nothing but minus 13.6 electron volt. Correct? This is what the given total energy, and we know that here kinetic energy is nothing but minus the total energy. So already my total energy is minus 13.6 electron volt. Then kinetic energy is nothing but minus 13.6 minus and minus plus 13.6 electron volt. Okay. Then potential energy is nothing but what? Potential energy is nothing but twice the kinetic energy. Okay. So calculate twice the total energy. So here 2 into minus 13.6, so that is nothing but 27.2 electron volt. This is what the answer with minus sign. Getting this? Write down one more question. Write down the question. Write down the question. Yeah. What is the maximum number of spectral lines emitted? What is the maximum number of spectral line emitted by a hydrogen atom when it is in the third excited state? When it is in third excited state. Okay, so what is the maximum number of spectral lines emitted by the hydrogen atom when it is in the third excited state? So we have to find out the number of spectral lines, maximum spectral lines when it is excited from third to ground. Okay, so here we have where it is excited from the transition of the spectral line obtained due to the transition of electron from n is equal to third excited means n is equal to 4 to the ground state, that means 1. Okay, so here we are calculating, we want to calculate number of spectral line. So we have the formula n is equal to n into bracket n minus 1 divided by 2. Okay, this formula we have. So third excited state to the ground state. So third excited state is nothing but 4. Don't take 2, 1. Okay, so we are only taking 4. So substitute n is equal to 4 n minus 1, that is 4 minus 1 by 2. That is nothing but 4 into 3 divided by 2. So here 2, so 6 spectral lines we will get. Okay, so here spectral lines are emitted during these transitions are 6. Getting this question? Okay, 1 mark question. Understood this? I hope now you are feeling simpler or easier. Okay, so now you can write down one more question. Okay, or okay, no problem. Next class we can, in next session we'll do other questions based on the atom. Okay, so I will end this session for today. Thank you for joining.